Okay, welcome to part 7. It's very important part, that is why I have written here 3 stars. Okay, now we are finding the Laplace transform of the derivative of a function. Suppose if the Laplace transform of f of t is f of s, then Laplace transform of the derivative of this function is that transform multiplied with s and subtracting the value of this function at 0. Now proof of this theorem can be seen at later point of time. Uh, Means in some other video I'll club all the proofs, okay, which are not delivered here. Right now I'm trying to use this theorem and find what is the Laplace transform of the second derivative. If I use it like that, what it basically says, Laplace transform of the derivative of this function is that transform multiplied with s and removing the value of this function, basic function, at 0. So Laplace transform therefore of the second derivative of this function is to be considered as f dash t dash. I am treating the second derivative, of course, as the derivative of the first derivative. Laplace transform of this one is s into the Laplace transform of this one, f dash t, this complete, as I am multiplying s with the transform, here s with the transform of this function, minus this function at 0, that is equal to s into, what is L of f dash t? Just now here it is s into f of s minus f of 0, so minus f dash of 0. On simplification it is s square into f of s, that is, for the second derivative you multiply s square for the transform of this original function, this basic function, minus s times of f dash of 0, okay, minus, sorry, it is f of 0 minus f dash of 0. Okay, you can take the screenshot for this one. Okay, using this theorem repeatedly, we get the Laplace transform for f double dash of t is equal to s square into the transform, whatever basic functions transform is there, square should be multiplied for the second derivative, and all the remaining terms are with minus, that is they are negative, and the power of s will fall down, that is 1 less power of s, start with the function value at 0, then minus 1s is again reduced, so s disappears and the derivative of the function appears. First function will appear, first term is only with the transform, remaining all the terms will be with the basic function f of t. So at 0 only we will calculate value of the function, value of the first derivative at 0, value of the second derivative at 0. If I write one more, you will get the clarity. F triple dash of t is equal to s cube into f of s. That is, for the third derivative of the function, the Laplace transform is given by multiplying third power of s with the transform. Only transform is used in the first term. Now s square with the value of the function at 0 minus s power 1 into f dash of 0, first function, next derivative, next second derivative, s power 1 will now reduce to s power 0, that is s will disappear and it will be f double dash of 0. For calculation of the Laplace transform of third derivative, this step stops at second derivative. Now you can tell what is the fourth derivative Laplace transform, that is s to the power of 4 f of s minus s cube into f of 0. S is decreasing, power of s should decrease one step every time, and here function value will appear, and then f dash of 0 will appear with one lesser power, minus s times of f double dash of 0 minus f triple dash of 0. I hope you understood. Now this particular the proof of this theorem we can delay and see at some later point of time. Right now I would like to go to the part of solving the differential equations using Laplace transforms. There in that part we will be using the derivatives of we will be calculating the Laplace transforms of the derivatives. Okay, now let us end up here. Better I will do one thing. Okay, I will tell you the alternate notation instead of using this. You take this screenshot for this. Now what is the alternate way of this? You can see here, if Laplace transform of this function is f of s, that f of s should be used. Instead of writing f of s, I can write L of f of t. So how this particular statement becomes now, using this concept here, L of f dash of t is s into L of f of t. L of f of t is this f of s, so minus f of 0. So L of y dash is equal to, instead of saying f of t, I'll just say y for that. So L of y dash will be s into L of y minus y of 0. Similarly, L of y double dash will be s square into L of y. L of y will appear only for first term. Remaining all, only y function appears. So minus the power of s decreases, that is s into y of 0. Start with y of 0, then increase the derivative order. Okay, so s, then s will be gone, y dash of 0 will appear. L of y triple dash will be s cube into L of y minus s square here, and L of y only first time. First starts with y of 0 here after this first term, minus s times of y dash of 0, then again s will be gone, minus all the terms are negative except the first term. So y double dash of 0. I hope if I write what is L of fourth derivative, I am clear that you will be having no confusion at all. S to the power of 4 L of y. Whatever fourth derivative you want to find here, the Laplace transform of fourth derivative of which function, you have to use the Laplace transform of that function, minus s cube into y of 0. Starting is y of 0 everywhere, minus s square into y dash of 0 minus s into y double dash of 0 minus y triple dash of 0. I hope you understood. Now this is how to take the Laplace transform of the derivatives of the function when we know what is the Laplace transform of that function. So if we know what is L of y, we can tell what is L of y dash and y double dash, y triple dash. So just if we know what is L of y, we will be able to tell the Laplace transforms of the derivatives of that function by knowing the value of that function and the derivative and the second derivative, so on like that, at the initial point 0, at t equal to 0. So let us end up. Thank you for watching this. Now we'll see how to find the Laplace transforms of integrals. Now this is talking about the derivatives. Okay, now this particular basic concept actually we will use in the solutions of differential equations. This is very important part of Laplace transforms, because this deals with directly the solutions of differential equations. So in the next part I'll tell you how to find the Laplace transforms of the integrals of the functions. Let's end up here. You can take the screenshot now.